All right, let's do an example. So we have the series the sum from n equals 1 to infinity of sine of n over 2 to the n, and we want to know whether our series converges absolutely, conditionally, or whether it diverges. Okay, so the way that we're going to approach this, let's start by looking at the divergence test. That's always a great place to start. So we're going to take the limit as n goes to infinity of sine of n over 2 to the n. We know sine of n lives between -1 and 1, so it's not going to be very big. And as n goes to infinity, 2 to the n goes off to infinity. So this is, the limit is equal to 0. We can think of this as coming from the squeeze theorem, if you would like. So -1 over 2 to the n is less than or equal to sine of n over 2 to the n, and that's less than or equal to 1 over 2 to the n. As n goes to infinity, this heads to 0, this heads to 0. So squeezed in between, we have sine of n over 2 to the n. So the divergence test doesn't tell us anything. Okay, so next let's try, let's shoot strong and try to show absolute convergence. If we find that it doesn't converge, then we'll have to come up with another plan, but maybe it'll work out. So we're going to take the absolute value of these terms. And when we look at this, I think a good place to start is thinking about the comparison test. Just like when we did the divergence test, we were thinking about comparing with 1 over 2 to the n. A similar thing can be used here. So 0 is less than sine of n over 2 to the n, less than the absolute value of sine of n over 2 to the n. And this is less than 1 over 2 to the n. Okay, for all n. Since the series 1 over 2 to the n converges by the comparison test, the absolute value of sine of n over 2 to the n converges to. And so we've worked out two things, both the series absolute value of sine of n over 2 to the n and the one that we're interested in, sine of n over 2 to the n, converges. Because convergence of the series with just the magnitude of the terms implies convergence of the series where we have signed terms. And from this we can conclude that since this guy converges, our series is absolutely convergent. Okay, so here are our basic options if we have positive and negative terms and we only care about showing convergence. So if we want to show that that such a series converges, if we're alternating, try the alternating series test. So the last example, when we looked at the series with terms sine of n over 2 to the n, for example, it wasn't alternating. We did have positive and negative terms, but they didn't bounce back one after the other. So that wouldn't have been an option there. The second thing is to try and show that the series is absolutely convergent. So you take the absolute value of all the terms and see if you can add them up. The third option is to find an expression for the partial sums. So, for example, if maybe we have something that telescopes or something like that. And that's about it.